India is a semiconductor design powerhouse. Nearly every major semiconductor company has a presence in India, designing some of the most advanced chips in the world. But once those designs are completed, they are sent to the United States, China, South Korea, or Taiwan to fabricate. It begs the question, why can't India fabricate any of the chips that they lay out? In the 1980s, the Indian government attempted to follow China, Taiwan, Malaysia, Korea, and Singapore in creating their own semiconductor manufacturing national champion. Things got off to a promising start, but then disaster struck. And the company, along with India's entire semiconductor manufacturing industry, hasn't recovered since. In this video, we're going to look at India's Semiconductor Complex Limited, or SCL, the national champion that failed. But first, please consider subscribing to the Asianometry newsletter. If you subscribe to the channel, you should also subscribe to the newsletter. Check out the newsletters for the full scripts, as well as additional commentary after the fact. You can find the link to the newsletter in the video description below, or you can go to asianometry.com. As of right now, you can expect a new newsletter every Thursday at 1 a.m. Taiwan time. Much thanks. Many of East Asia's semiconductor industries can trace their roots to Western electronics companies relocating certain outsourced factories there in the 1960s. In the mid-1960s, Fairchild Semiconductor seriously considered putting a factory in India, but the famously formidable Indian bureaucracy scared them off, and they eventually opted for Malaysia and the Philippines. As the pace of technology quickened in the 1970s and 80s, the Indian government identified microprocessors and other types of semiconductors as the potential foundation for a new revolution. They decided they had to have their own horse in the race. Thus, in 1984, the Indian government founded a 100% state-owned enterprise, the Integrated Device Manufacturer, SCL. SCL's goal was to eventually design and manufacture leading-edge circuits and electronics. Their vision was that the company could be the foundation for a native Indian electronics industry. The government invested somewhere in the neighborhood of 40 to 70 million USD into the venture, quite a lot of money at the time. The company would be headquartered in the planned city of Mohali in the state of Punjab. At the time, the Punjab economy was mostly agricultural based, but the area was up and coming. It was emerging as an electronics industry center with major units like Punjab Wireless Systems and Punjab Communications Limited based there. To fill the ranks, SCL hired young graduates from top technical universities like the Indian Institutes of Technology and the Indian Institute of Science in Bangalore. These universities have strong links to the West and have trained a very strong pool of skilled engineering talents to draw from. The IIT Bombay School in particular has long had a very good electrical engineering course. They were also able to recruit from esteemed Indian electronics companies like Bharat Electronics Limited, the Indian state-owned aerospace and defense electronics company. There are many factors that go into creating a successful, high-performing semiconductor factory. I have reviewed a few of these in prior videos, but you can summarize them into 4 categories: financial capital, human capital, government/infrastructure, and manufacturing technology. First, you need to have the money, a lot of it, so to pay for extremely expensive chip manufacturing equipment, notably in the photolithography space, as well as chip testing equipment. All of that stuff has to be constantly upgraded and maintained as it is used. That also costs money. In India's case, all of these have to be imported from places like Europe or Japan. Import duties and documents have to be addressed and streamlined. You need to have smart, well-educated people to run your fab, skilled labor who can quickly gain familiarity with the expensive equipment and how to use it. Additionally, you need PhDs doing R&D to learn new processes and push the company forward. India is quite strong here. You need to have substantial, near 100% government buy-in, as well as stable power and water supply. There are also environmental concerns. The manufacturing process is quite toxic. India has challenges here. The government buy-in is there, but the infrastructure isn't. A single power outage or water shortage can ruin months of hard work. And lastly, if you want to quickly catch up with the rest of the industry, you need some way to acquire older process node technology for yourself. Don't reinvent the wheel. SCL wanted to be a leading semiconductor manufacturer, and as I mentioned, the playbook for doing so is pretty well established. They had sufficient financial capital, smart people, and government buy-in. Now was acquiring the older technology. So you strike a technology transfer deal with a more advanced company, get them to teach you how to do it, and hopefully before long the student can become the master. World-class semiconductor companies know this, of course, and so they very closely guard their technology process nodes and trade secrets. Technology transfer agreements are almost always for older processes and never for the leading-edge stuff. At SCL's founding in 1984, they were able to license a 5-micron process technology from American Microsystems Inc. AMI was nothing like Intel or Motorola, but it was a start. Shortly thereafter, SCL was able to acquire process technology from 2 other companies as part of a deal to manufacture electronics components for them. The first deal was with the American industrial automation company Rockwell for the purpose of making their 2560G microprocessor. The second deal was with the Japanese firm Hitachi for the purpose of producing components for their electronic wristwatch. The company also performed third-party assembly duties for electronics brands. Notably, they assembled the BBC, yes, the broadcaster BBC, Acorn computer for the Indian government's Computer Literacy and Studies in Schools program. These technology transfer agreements allowed SCL personnel to travel to the US and Japan for in-person training and learning. SCL quickly disseminated this info to the rest of the company. They augmented this trade knowledge with university academic partnerships. Using these resources, the company advanced very quickly from the 5-micron process technology down to a 0.8-micron process in the late 1980s. 0.8 microns, or 800 nanometers, was first achieved in 1987 by leading companies like NTT, Toshiba, and Intel. So at this point, SCL was one semiconductor generation behind the leading edge. It seemed possible that India could achieve its goal of being a global semiconductor manufacturer within a decade. Those hopes ended in 1989 when a devastating fire broke out at SCL. The cause of the fire remains unknown. A few sources have claimed, without evidence, that it was arson, which I guess can make sense since SCL was making processors for the military at the time. But semiconductor fires are not rare. From 1986 to 1995, insurance records show that fires are one of the most common causes of operational losses in the industry. Many of these chemicals are flammable. Most likely the incident was an honest accident. Regardless of the cause, the fire was a devastating setback for India's semiconductor manufacturing efforts. Fires are so devastating because the burning chemicals are toxic and release corrosive gases. The fire then triggers the water sprinkler system, causing even more damage. It would take until 1997, 8 years, and substantial financial investment well north of $50 million, before production finally restarted. By then, new entrants like TSMC, which was founded in 1987, and Samsung had entered the race, and they quickly raced ahead of the rest of the world, capturing critical global market share and scale. India lost untold amounts of progress. The government subsequently lurched through failed proposal after failed proposal in order to try to make up for lost ground. They wanted to sell the fab, but potential private investors could not come to an agreement with the Indian government on terms. They then retooled the fab from making chips for telephone exchanges to making chips for smart cards. This didn't really take either. Then finally, in 2005, the company was restructured as an R&D center within the Department of Space. SCL would be renamed to mean Semiconductor Lab. This finally ended SCL's chances at being a competitive commercial entity. But the company had long been out of the race. Much of its revenue came from government contracts. SCL's offerings were not even competitive in the domestic Indian market, let alone abroad. But even with the government as a captive customer, the company could not turn an attractive profit. There were no economies of scale. In the 2005-2006 financial period, the company produced 1,000 6-inch wafers, but had 20 times the installed capacity. In 1999 to 2000, SCL made $14 million in revenue and just $400,000 in profit. In 2005 to 2006, its final year as a company, SCL made $3.5 million in revenue and turned a loss of $2 million USD. The year before, the company turned a stunning $5.6 million USD loss. its restructuring was a kind mercy. Today, SCL mostly does R&D work with its old 6-inch wafer fab. Recently, in 2019, they announced that they were able to accept chip designs at the 180 nanometer node. This is nowhere near the leading edge, but of course, there are plenty of viable commercial cases for fabbing semiconductors at higher nodes. Skywater Technologies, a publicly traded American foundry that I have previously profiled, runs a 130 nanometer node. The more critical issue has to do with extremely sluggish development. It took SCL nearly a decade to reach that 180 nanometer node. They have been working on it since at least 2011, when they paid millions to Israel's Tower Jazz Semiconductor for a fabrication unit. SCL in the early 1980s had the advantage in that everyone else in the rest of the world was not too far ahead of them. Taiwan and China had yet to move into semiconductors, and the equipment back then was a lot cheaper. But even back before the fire in 1989, SCL was starting to experience the financial strain of competing in the semiconductor business. The costs of going to 800 nanometers had forced them to drop the BBC Acorn computer project. Talented SCL personnel were constantly leaving for better jobs in the private sector or abroad. For India, the sheer amount of capital needed to build competitive, productive fabs has been cited as the single most significant obstacle in establishing a viable semiconductor manufacturing industry. Today's leading-edge chip factories regularly run up into the tens of billions of dollars. This trend really started to ramp up at the 14 nanometer node generation, and it is only getting worse. Even for the biggest private Indian entities, companies like Tata, Reliance, and such, this is hard to swallow. Reliance Jio initially spent 15 billion USD on their nationwide LTE data network over the span of 4 years. TSMC will spend $20 billion on just 1 gigafab over 2 years, and right now they're building 3. All that investment has to pay for itself, and in the volatile electronics world, that is not always a given. Regardless, the Indian government has since attempted to revive the country's semiconductor manufacturing efforts. All of these efforts have failed. For instance, in 2006, the country announced a $3 billion Fab City project for manufacturing. AMD had been interested in putting an assembly and test facility there until bad industry conditions shut it down. In 2013, the Indian government lifted custom duties on all imports of parts and machinery related to semiconductor manufacturing, but this did not seem to have helped to jumpstart any foundry efforts. In 2014, India approved a proposal from 2 investor groups to build fabs in India. Both projects together would cost about $10 billion. The government would have provided ample financial support, up to 25% of the total cost in interest-free loans, tax breaks, and subsidies. The first consortium had some notable names: Jaiprakash or JP Associates Limited, Israel's Tower Jazz, and IBM. JP Associates is a large Indian conglomerate in the construction, power, and real estate businesses. But in 2016, JP and its group pulled out of the project. The firm had a lot of debt and said that a semiconductor plant was not commercially viable at the moment. The second consortia was led by a company called Hindustan Semiconductor Manufacturing Corporation, or HSMC. The investor consortium had tapped chip-making expertise from European chipmaker ST Microelectronics and Malaysian state operator Silterra. The second team also did not pan out. In 2019, the government canceled HSMC's 2-year-old letter of intent. The consortium had to submit documents for demonstration of commitment, but had failed to do so. An interesting coincidence, a year later, another semiconductor company named HSMC, this time standing for Hongxing Semiconductor Manufacturing Company, raised millions to start a fab in the Chinese city of Wuhan. A similar lack of execution, in addition to a pandemic, ended up trashing that too. Since then, no serious Indian proposal has emerged, and that is despite the current market conditions. I want to re-emphasize that India retains world-class chip design capabilities. Tens of thousands of Indian engineers work directly in VLSI design, and their chips are taped out in leading-edge fabs around the world. Virtually all the world's biggest fabless chip companies have an Indian presence. Since the mid-1980s, the design and manufacture of chips have split apart. It is no longer necessary to do both at the same time. And increasingly, few companies and economies are capable of doing so anyway. so India's powerful advantages in design should be commended, and I hope to do a video about it in the future. With that being said, SCL's failure to stand on its own as a commercial entity has had long-term consequences. Today, India lacks substantial semiconductor fabrication capacity. In fact, there is hardly any semiconductor fabrication capacity at all. As of this writing, 100% of India's chips, logic, memory, all of it, have to be imported from abroad. In 2019, India imported $21 billion worth of semiconductors, according to the India Electronics and Semiconductor Association. This number is growing at about 15% a year. In 2020, the country fell prey to the worldwide semiconductor shortage, disrupting a variety of critical Indian businesses. For instance, India is the world's second largest smartphone maker. That lucrative industry grinds to a halt when the right chips are not available. Furthermore, a significant portion of these imports, 37% in 2019 or $7 billion worth, come from China. This has critical geopolitical repercussions. Sino-Indian relations today are tense, and further disruptions may come about. To conclude, there is no shortage of ideas and human talent for possible approaches to bring semiconductor manufacturing back to Indian shores. But there must be consistent, long-term direction from the very top, and fountains of money committed to that direction. For India, the market has long passed the phase when a private entity can seed a thriving semiconductor manufacturing industry without outside help. The government has to do more to catch up. Alright everyone, that's it for tonight. If you want more content, you can like and subscribe to the channel. The feed will show you a bunch more new videos like this one to watch. And remember to check out the Patreon if you want to support the work and watch any of the early access videos. Want to send me an email? Drop me a line at john@asianometry.com. I love reading your emails. And if you live in Taipei, I would love to sit down and grab a coffee sometime. Until next time, I'll see you guys later.